Okay, now we have it. Let me mute Randy here.
Yeah, Mondays and Wednesdays I'm in call.
Randy, are you talking to me? Okay.
Yeah, I'm here.
Yeah, okay, good. So your mic was on. Are you trying to ask a question, or you just you left your mic on accidentally?
Oh, sorry, I left it on accident.
Okay, thanks. New syllabus version 11, upload to Canvas, and I want to cover chapter 21 in the first hour, and then we will do the virtual lab, right? Virtual. I prefer make-believe lab. Make-believe lab. Okay. After Mr. Rogers, right?
Professor,
Yeah.
I just have a quick question about Lab 3. So
Yeah.
we were trying to upload the graphs into the Google document and it comes out kind of weird, and we don't want you to get the messed up graphs. So should we just screenshot it and take a picture so it uploads as a picture so it doesn't change?
Okay.
That'd be better.
Well, you don't have to worry about that, because what you see is not what you get whenever you double click in the Google Drive. Okay, so you don't have to worry about that, because I have seen that. I'm sorry, I'm under the weather here. My throat is scratchy. My experience with Canvas, with Google Drive, is that when you open an Excel document in Google Drive, the graphs, they don't show like the way they're supposed to show, okay? So you don't see what you get whenever you click inside, whenever you open your Excel document inside Google Drive. However, when you download your hard drive, like I do all the time, I see the graph in a completely fine way, okay? So you don't have to worry about.
Okay, so if it is weird, you'll just let us know and then we can show you that we did it right. If
Yeah,
there does
well,
happen to be an issue.
Yeah, if it is weird, you're gonna have your hard copy, right? Your hard copy report,
Right.
which is gonna show the graph in a proper way. Okay. So
Okay.
I'll double check with the hard copy. Let me check here. The group 01, right?
Okay, thank you.
Yeah. So you don't have to worry about that. Sometimes they like this one, sometimes the graph doesn't show properly in how do you say, in Google Drive. Now this is group number 1, for instance, right? For instance, I don't see the R square and the regression equation here. Let's see what this group did. Most likely this group did it right. Okay, and just it doesn't show properly in the Google Drive. That's going to be lab number 2, right? Lab number 2. See, I don't see any. Oh, must be the wrong file. Yeah, is that the raw data? That's the wrong one. Lab number 2, group number 1, right? Lab number 2, group number 1. Let's take a look. Must be this one. Let's take a look here. Yeah, see? You can see that they have the R square and the regression equation here. That's because I downloaded to my computer. I opened inside my computer, but it doesn't show correctly in Google Drive, right? Even the graph itself, the graph was supposed to be a decreasing function. It's not even showing a decreasing function. It's showing an increasing function. So I just don't, I don't rely on opening the graph in Google Drive. So you don't have to worry about that. Okay. It's just that they have to correct that in Google Drive. They didn't do that yet. It has been like that for years already. They didn't do anything about that yet.
Right. And there is a question in the chat about when Lab 3 is due.
Okay, well, Lab 3 is due today. Okay, it's always due before the next lab meeting. Okay, so that's when the lab 3 is due. Let's go back here. The other labs were not due right away because, for instance, lab 2, right? Lab 2 was not due on the following Wednesday because you had an exam, and I let you turn in before lab 3, right? Now lab 3 is due today because we do not have any other funny activities before. Okay.
Professor,
Yeah.
there was actually a little bit of confusion on whether lab 3 was due today or not, or if it was postponed. So we didn't even prepare it yet. Is it possible to turn it in the next time?
Let's see. Okay.
Yeah, because
so
we're in the impression of like turning it in because like I felt like there was like no due date on it, so we just kind of like did partial.
Okay,
Yeah, it was
so
a
let's
little bit
do that.
confusing.
Lab 3 and 4 do this time, okay? But then from now on, make sure you turn in the lab in the next lab meeting, okay?
Thank you. We appreciate it.
4 do, okay? Let's do this way. Lab 3 and 4 do,
Appreciate it, Professor.
okay? For everybody. And and then lab 4, what's gonna have? Today is lab 4, right? Lab 4 is going to be due before lab 5, right? And then lab 5 is going to be due before lab 6. Do you see how much time you have to do lab 5, right? Okay, we don't turn in lab 5 the next week because it's a spring break. And you don't turn in lab 5 the following week because it's an exam, right? So you have like 3 weeks to turn lab 5. Lab 6, right, should be due just before lab 7 and so on. Lab 7 before lab 8, lab 8 before lab 9, right? And lab 9, I'm going to decide when is it going to be due because it's the last lab that is scheduled here. Do we have a holiday today? And I'll let you know when you get there. I would say, you know what? Let's put lab 9 due at the last day. Do lab 9 due. Lab 9 due. Like that. And I'm going to save this one as version 12.
Oh, and Professor,
Mhm.
sorry, one more thing. When you get a chance, just because with the quiz, with the third question, I was looking back over the notes and it was kind of hard to tell like how you're talking about there's no battery, but it was in your slideshow with the pictures. But if you could merge that into our regular notes document, that would be really helpful.
Yeah, I'm quite sure that I had written down that in no battery, okay? But we can talk about that during the office hours, okay? I can show, I wrote that down here somewhere in the notes about both the charging and discharging, okay? But you are asking what? You're asking that that information was not in the notes. That's what you said?
No, because because in the last office hours right after the quiz, we looked at it, but then you also pulled it up from your pictures and how you explained it from your pictures.
Oh,
Does that make sense how I explain that?
Well, what you must have seen, okay? Is that the RC circuit? Let me get the RC circuit here. That's the one. No, that's not the one. Okay, RC circuit. Okay, here is the discharging case. Okay, there's no battery in there, and then there's this other illustration in which you are charging the capacitor, and the battery is in there. See that? That's the charging one. Okay.
Right. Do we have access to this?
Well, you have access to the video, right? You have access to the video. Charging RC.
Right. No, yeah. So I was just curious because it like how our stuff is open notes and whatever. I mean, I can like edit it, but I just thought for the sake of not just myself, but other people as well, I thought it could be helpful for the class if that was typed into, I believe it was page 47 at the end of the
Yeah,
notes.
I'm considering turning this thing into a PDF file and upload it as a separate file. Okay, instead of okay, I'm
Because it
considering
would just be just because it can be, I could see how this PowerPoint could be kind of hard to follow if we don't have you to kind of explain what's going on in the pictures.
Okay, and also notes. Oh yeah, I would consider that, and
Right, thank you.
you might have a this document also available in PDF. Okay, so what we have here. No. Okay, so this is note 7. Let's go for chapter 21 and what we did so far, chapter 21. Well, first, magnetic fields. Okay, that was the first section in this lecture. So, yeah, magnetic fields, 21.1. 21.2 is something else. Okay, it's magnetic force, but this is magnetic force is specifically applied to a moving charge. Okay, what we did here for magnetic fields, we know that there is a magnetic field which is an invisible entity, but we can measure it, and there is also a magnetic force among magnetic bars. Okay, magnetic bars. That's what we covered last time. In addition to that, there is also something else that you have to know. There is also a magnetic force applied to moving charges, moving electric charges. Okay? So it's different. This force here is sort of different from this other force, right? You do have a magnetic force between magnetic bars, but in addition to have this force, you also, let's go ahead. Here you go. Here's the magnetic force between magnetic bars. And magnetic bars are like what we call magnetic dipoles, which is the magnetic counterpart of the electric dipole. So in addition to this force among magnetic among dipole bars, magnetic dipole bars, we also can find the force. We can also observe that in experiment, okay? And that's another law of physics, that there is also a force applied to a moving charge, but it has to be a moving electric charge, and the charge must be moving in a specific way. If the charge is at rest, like this one that you see here, there is no magnetic force whatsoever. The magnetic force is going to be equal to 0. Okay, so remember, the magnetic force occurs, magnetic force on a charge occurs whenever you have a moving electric charge. But the electric charge must be moving in a specific way too, because if the electric charge is moving in a direction parallel to the magnetic field, the force is still 0. Okay, the force is still 0. So how does the charge must be moving? Okay, the charge must be moving in a direction other than parallel to the field. For instance, if the charge is moving, the vector velocity of the charge is perpendicular to the magnetic field lines, then you have the largest force, the largest magnetic force that you can have. And that's a law of physics. And this force is given by QVB. QVB. But that's just the magnitude of the force. You must also have the direction of the force. What is the direction of the force? Okay, the direction of the force is going to be perpendicular to both the magnetic field and the direction of motion of the charges. It's actually given by the right-hand rule. Okay, so the way you do it, the direction of the force is given by the right-hand rule. How do you do that? You lay your hand along the direction of the velocity vector of the charge, your right hand, it has to be your right hand. Move the palm of your hand towards the direction of the magnetic field, and your right thumb points in the direction of the force. Okay? The book describes that, the right-hand rule, and you must have a nice illustration here. Here you go, right-hand rule, see that? Okay, here you go. Interesting, they're doing the right-hand rule in a different way here. Huh. Interesting. There are more than one way of doing the right-hand rule, okay? Let's go up. Yeah, see, they do the right-hand rule in a different way, but it also works. Okay, in the case of the book, how do they do the right-hand rule? Okay, the vector velocity, the velocity vector is pointing along the thumb. The magnetic field points along the palm, the fingers of the palm of your hand. And when you orient your hand properly, the magnetic force is going to be perpendicular to the plane of your hand. That's another way of using the right-hand rule. Other ways of using the right-hand rule is lay the palm of your hand along the velocity vector, move it towards the direction of magnetic field, and the thumb points in the direction of the magnetic force. Okay? And in mathematical way, in vectorial, there's also magnetic force applied to the moving electric charge. Okay. According to the following. Here you go. If the charge is at rest, there is no magnetic force. Okay. If the charge is moving parallel to the magnetic field lines, there is no magnetic force either. However, if the charge has a velocity vector component that is perpendicular to the magnetic field lines, there will be a magnetic force. Okay. The force will be maximum whenever the velocity vector is perpendicular to the magnetic field lines, and given by magnetic force QVB. Here you go. If the velocity vector makes an angle theta with the magnetic field, with the B field. Comma, the magnitude of the magnetic force will be what? And magnetic force Q B B, and that will be a sine of the angle theta here. Okay, that's just the magnitude. That's just the magnitude. Okay. That's just the magnitude, right? The direction of the force is given by the right hand rule. There are several ways. There are several ways of spelling out this rule. The one that I'm most familiar with and most books teaches you is the following. It's like the following. Given by point the palm of your right hand along the direction of the velocity vector. Here you go. Initially, point the palm of your right hand along the direction of the velocity vector to move the palm of your right hand towards the magnetic field vector. Vector 3. The direction of your thumb, of your right thumb, will point in the direction of the magnetic force. That's one way of using the right hand rule. Note that your book has a different way of using the right hand rule. Okay. RHR. But the final result is the same. The final outcome, right, is the same. And now let's play a little bit, right? Let's play this is another law of physics. This magnetic force equation is another law of physics. Another law of physics. So now we have the following laws of physics. Now we have the following laws of E&M, electricity and magnetism. We have, yeah, here you go. Those 1, 2, 3. Now we have 3 laws of electricity and magnetism. The flux of the electric field is equal to the charge enclosed by the Gaussian surface. The flux of the magnetic field is equal to 0. Flux of the magnetic field, through a Gaussian surface also is equal to 0. And we have this other one here. Okay. For the third equation, I'm going to emphasize here for the third equation. For this third equation, comma, the direction of the magnetic force is given by the right-hand rule. Okay, let's take a look in the internet of other right-hand rules. Okay, that's one way of spelling out the right-hand rule. The thumb is pointing in the direction of the vector velocity. The palm of your hand is pointing in the direction of the magnetic field vector, and the magnetic force is going to be perpendicular to the plane of your right hand. Okay, another way, right hand rule. There you go. Let's see. Wikipedia. Okay, here goes. If you have vector A and vector B, right? Vector A will be V, the velocity vector of the magnetic force, and vector B would be the magnetic field vector. This is another way of spelling out the right-hand rule, which is similar to that one that I mentioned to you, the palm of your hand along the velocity vector, and then you move the palm of your hand towards the B field, the B vector. What you see here is a vectorial product. And by the way, the magnetic field is, the right way to write down the magnetic field is in terms of a vectorial product. Let's see here. Okay, or in a vectorial fashion. Okay, Q, V, and then we're going to have the B vector as well. And we must have the vector product, the vectorial product here. Oh, here you go. That's the one. No sign of theta, because the vectorial product already implies that there is a sign of the angle. Theta, don't forget, is the angle between the B field and the velocity vector. Okay. The angle theta is the angle between the velocity vector, the velocity, and the magnetic field vector. The velocity and magnetic field vectors, when they are placed tail to tail. Okay. Note, see, now going back here, right? If looking at this equation here, if theta is equal to 0, right? Consequently, the force is going to be equal to 0 as well, right? Sine of 0 is 0. And if the velocity of the charged particle is 0, the magnetic force is also going to be 0. So everything that we mentioned in the illustration applies to this formula here. It is encoded in the formula. Encoded in. So here we go. And what is the velocity has a component, right? Here you go. The velocity has a component along the B field. We have a force that is slightly smaller, given in terms of the sine of theta that you have already seen. Here's the representation, the vectorial representation of this force. But the direction of the force is still going to be the same. It's just the magnitude is going to change. It's just the magnitude is going to change. What you see here is the representation of a vector coming out of the plane of my screen. Okay. Let's look at this one here. Now, suppose just another way of looking at the force that's being applied to the charge. Okay. Here in this case, the magnetic field is in the plane of the paper, right? Pointing upwards. What if I rotate this picture and now the magnetic field points towards you, away from the plane of my screen, of my display? Okay. And let's say the charged particle has a vector velocity that's still perpendicular to the magnetic field line. You go ahead, do the right-hand rule, V, V cross B, the force is going to be perpendicular, simultaneously perpendicular to the velocity vector and the magnetic field. Okay, and what does it mean about the motion of the charged particle? Okay, every time that you have a force that's perpendicular to the velocity vector, and provide that this force is uniform and is constant, okay, this particle is going to undergo a circular motion. Okay, this velocity vector is going to change direction. That's how we should look at that. Okay, so here you go. Oh, I can put more. Oops. Group, let's see if it's going to work. If this charge moves a little bit further, right? So let's say here. Now you can start seeing a type of circular motion. Okay. So let's document that in the notes. The vectors, when the vectors are placed tail to tail. Okay. According to the above equation, the magnetic force will always be simultaneously perpendicular to the velocity vector, the velocity and magnetic field vectors. Okay, motion of a charged particle subjected to a uniform magnetic field. right? Two cases we're going to do. Velocity vector perpendicular to the B field. Okay. Velocity vector with a component perpendicular to the B field and another component parallel to the B field. Okay, so two cases. Okay. In this case, the charged particle will undergo uniform circular motion, just like you saw here. Here's a uniform circular motion. Okay, here you go. It's uniform circular motion because the magnetic force is perpendicular to the velocity vector. And what if we have a component? Unfortunately, I do not have an illustration for this one. Maybe your book has. Let me take a look. Not this one. What if the velocity has a component that's parallel to the magnetic field? What's going to be the motion of the charged particles? Motion of charged particles in a magnetic field. All right, that's here you go. Velocity vector perpendicular to the let's see. We have an electric field here. He put an electric field. I guess he meant no. Okay, he's comparing the electric force with the magnetic force. Okay, here you go. Velocity vector perpendicular to the magnetic field. We have a section of a circle within this region. Okay. And what if the velocity vector has a component along the magnetic field? Here you go, the same illustration that you saw there in my slides. Okay. And then let's see if he has for velocity. Doesn't have, we'll do it in my notes. Okay, well, it doesn't look like it has. I'm going to put that for you. You undergo uniform circular motion. Velocity vector with a component with one component perpendicular to the B field and another component parallel to the B field. It's still going to be kind of similar, okay, but it's not exactly the same. In this case, the charged particle will undergo a helical motion. It's still a uniform circular motion. It's still a uniform circular motion, but the plane of the circular motion is moving with that component of the velocity vector, okay? This is still a circular motion, but the plane of the circle of the particle is moving with a speed equal to the component of the velocity parallel to the B field. Like that. Let's see if we have one here. Helical motion of charged particles. Helical motion of charged particles. It's always good. Oh yeah, we have one here. A charged particle.
91% dos nossos clientes recomendam o Rosinha.
Okay, so here you go. Here's an illustration of the helical motion of the particle. Okay, we have this velocity vector here that has a component parallel to the B field and another component perpendicular to the B field. The particle still is going to describe sort of a circular motion, but it's a circular motion that the plane of the circle moves along the direction of the B field. Okay? And we are assuming that the magnetic field is static and constant. Let's see if he has more than that.
So guys, let me tell you the topic for this video. So you can see the title, details about the helical motion of a charged particle in a static magnetic field. Before going to the helical motion, this is a very important topic, frequent topic. Before going into that, we'll see that how does a charged particle behave if it enters some static magnetic field. So it can enter in a perpendicular direction. The charged particle enters in the direction.
Yeah, we don't.
So you can see in this figure.
Okay, we can stop here. The important thing here is this illustration that he made. Okay, and this type of motion is spelled out. Let's see if we have a better one. Helical path of charged particle in a magnetic field. Let's see here.
Now let us consider a case where velocity of particle makes an angle with the magnetic field.
All right, so here you go. Velocity of the particle, one component is parallel to the B field, the other component is perpendicular to the B field.
Resolving velocity into components, we can say that due to perpendicular component alone, the particle will follow a circular path.
Yeah, here you go. Nice, right? I like that. Okay, so the force is going to point towards the center of this circular path, but don't forget that the particle still has a component along the B field.
Such that the circle lies in a plane perpendicular to the magnetic field.
Here you go, the velocity component along the B
But the
field.
particle also has a component of velocity in the direction of magnetic field. We know that a particle moving parallel to the magnetic field does not experience any magnetic force, and thus its motion is not affected. Therefore, resultant motion of particle
There you go.
will be the superposition of the motion due to each component of velocity.
That's a very good simulation. I like that. Here you go.
Note that it is a common misconception that the point of start of helical path lies on the center of helix.
No.
However, the point of start
Doesn't lie in the center of the helix. Lies on the outside of the helix, on the path of the helix,
is at the edge of the helix.
the edge.
Also note that both the components of velocity are perpendicular to the magnetic force, and thus resultant velocity is still perpendicular to the magnetic force.
That's a very good simulation. There you go. Velocity vectors, force vectors, magnetic field vector, and the path of the particle.
and thus work done by magnetic force is still 0. Now, radius of circular path is the radius of helix, and this distance between two successive cycles is called the pitch of helix. Radius of circular path depends only on the perpendicular component of velocity, and pitch is equal to the distance traveled by the particle along the direction of field in one time period of circular motion. That is, it is equal to this term. Here, time period of circular motion does not depend on the velocity of particle. Therefore, pitch of helix depends only on the parallel component of velocity. So for the given velocity and angle, ratio of pitch to radius of a helix will be equal to this term.
Do you love Gantt charts? Here's how easily you can build one in click.
Good. Come on. Okay, it's over. Okay, I'm going to post this link here. I like this video. This, you can. So I like so much that I'm going to put here in the notes if you want to. Simulation of the helical and circular path of a charged particle subjected to a magnetic field. Simulation helical and circular path of a moving charged particle subjected to a magnetic field. If the idea is still not clear in your head, right? Take a look again at this simulation, which is pretty good. Another way to visualize this helical paths is by envisioning the circular plane of the particle, of the path of the particle, moving along the B field direction with a speed equal to the parallel component of the component of the velocity vector, parallel to the B field. Okay. That's one. That's what we have for this section. Let's take a look at 9:44 right now, right? Let's see if we can do a quick example here. Okay, what are the applications of this type? Let's just write it down. What's the applications? What is a real life? What is a real life application of this type of motion? Okay. What's a real life application of this type of motion? One real life application is in the auroras. Auroras is related to this type of motion. The auroras that we see in the northern and southern portions, and other southern portions of the Earth nearby the poles is a result of this type of motion. Okay? So how does it go? Okay, auroras, huh? Let's take a look here, auroras. Aurora, northern lights, right? Northern lights, that's another name for that. And let's take a look at Wikipedia too. There are the northern lights, and then there are the southern lights. How do they occur? How those northern and southern lines occur? As you see, they have an illustration here. It has all to do with the motion of charged particles at the high altitudes in the atmosphere. Okay, so those displays that we see has to do with that. Let's see if they have here. Yeah, I have to look at another place. Charged particles trapped in the Earth's magnetic field. Yeah, magnetic field. The Earth's magnetic field. Let's see. I think they have an illustration here. Oh yeah, here you go. It was more or less like that. See the helical path? I don't like this website. It's a NASA website. But the way I'm going to describe in words, if I cannot find an illustration, illustrations are very good to better visualize a difficult phenomenon. Earth's magnetic field trajectory trapped in my Earth's magnetic field. Let's see if they have anything here. No, they don't. Too bad. Oh yeah, this one. This one is better. Okay. Here you go. Here's the Earth's magnetic field. Okay. Here's the Earth's magnetic field. You know, you can also have other magnetic field lines closer to the pole, right? And then what happens? What happens is that the sun emits charged particles. That's what we call the solar wind. The same solar wind that's responsible for disruption in the communications here of the Earth. Okay, so charged particles coming from the sun, which is the sun, which is the solar wind, ends up trapped in the magnetic field of the Earth. As they get trapped, they undergo this helical motion along the magnetic field lines. It's not as in the case of the Earth, it's not a uniform magnetic field, but it's still is a kind of a similar type of motion because the particle is moving in a helical path with the magnetic field lines at the center. Okay. So as the particles move closer and closer to the surface of the Earth, what happens? They start to collide with the gases of the atmosphere, and those charged particles are so energetic, they're flying so fast that they react with the nitrogen and oxygen of the atmosphere, making that gas glow. This type of phenomenon we observe only nearby the poles, okay, because of the feature, because of the way that the magnetic field of the Earth is distributed throughout, okay? And we have another one. Okay, so northern lights. That's one way. Real life application is the northern lights, northern and southern lights, or auroras, or auroras. The auroras we see the northern southern portion of the Earth nearby the poles as a result of this type of motion, charged particles. So the step by step is like that. The sun emits charged particles towards the space. Okay, the so-called solar wind. The so-called solar wind. Some of these charged particles interact with the Earth's magnetic field and becomes trapped. Okay. As they are trapped, they move in a helicoidal path, bouncing back and forth nearby the poles, nearby the geographic poles of the Earth. These particles are traveling very fast, and as they reach Earth's atmosphere, okay, they collide with oxygen, nitrogen, and even they collide with the CO2 as well. Okay, carbon dioxide in the atmosphere, even though it's a very small quantity in the atmosphere. Okay, these collisions causes the molecules to glow, and the color of the glow depends on the type of molecule that collided with the charged particles emitted from the sun. Okay. 9:53 right now. That's one of applications. There are more. Okay. There is what we call the mass spectrometer. That's another application. Is another application of this type of motion. We're going to talk about the mass spectrometer. Okay, and let's see if I can have another one here for you. Oh yeah, here's the velocity selector. The book doesn't cover the velocity selector. The velocity selector is used in conjunction with the mass spectrometer. And here you go. Here's the mass spectrometer. We have a charged particle entering the device, the mass spectrometer itself. Before it enters this region, here we have a region of magnetic field. And here, we also have a region of electric and magnetic field. In this case, the electric and magnetic field are tuned in such a way that the particle moves in a straight line and can go through this gap in the device. Okay. When the particle is subjected only to the magnetic field, what is going to happen? This particle is going to describe a circular motion, a circular pattern. Okay. And we have here in this device, we have a phosphorescent screen. And when this charged particle collides with this phosphorescent screen, it's possible to see a glow, just like we see the glow of the northern lights. So the scientists measure this distance here, know the radius of this circular motion, and can extract information about the mass and the electric charge of the particle. Okay, so it's 9:56 right now. Any questions about that? What I'm gonna do, we're gonna have our break, but before we have our break, I am going to take attendance. And today is going to be lab attendance. Interesting. Check one thing here. Syllabus. 20 seconds. Well. Okay, Arthur Pacheco, are you there? I don't hear from Arthur Pacheco. I'm going to put a star here in his name. And Elika, are you there, Elika?
Here.
Thank you. Brianna Valencia. Brianna, I don't see Brianna in my list. Justena Youssef. Are you there, Justena? I see Justena in my list. I'm going to put a star here. Ashley, are you there?
Justena said she's here on the chat.
Can you repeat, please?
I was saying Justena put that she's here on the chat. You just didn't see it.
Let me. Oh yeah, that's right. It's hidden here, my chat window. Thank you. Justena is here. Oh, Pacheco too, right? Pacheco also. Here you go. Thank you for telling me that. Ashley, are you there, Ashley? I don't see Ashley here in my list. Natalie Spinoza. Thank you, Natalie. Jeanette Garcia. I don't see Jeanette here. 60. Randy Bautista.
I'm here.
Thank you, Randy. Noor. Noor is also here, right?
Yep, right here.
Thank you. Kaylee Hernandez. Thank you, Kaylee. Kennedy Lindsay.
Here.
Thank you. Ryan Ong. Thank you, Ryan. Donia.
Here.
Thank you, Vanessa Bonilla. Next is Blanca Hernandez.
Here.
Thank you. Antonio Jimenez, Joshua Antonio Jimenez.
Here.
Thank you. Alondra. Thank you, Alondra. Daisy. I don't see Daisy here in my list. Yesenia. I don't see Yesenia either. Okay. Next is Labelut.
I'm here.
Thank you. Let's see. 15. Yeah, good. We have the right number here of people. And let's go ahead and take our break. 9:59 right now. Almost. Oh, now it's 10 o'clock. Break from 10 a.m. to 10:15. You know, while we're at the break, make sure to download the spreadsheet for lab. What's the lab numbers today? Lab 4. Lab 4 from your group folder. Okay, and I'll see you in 15 minutes. I'm back here. Lab number 4. A reminder. Reminder, lab 3 and 4 are due next week, March 29. Remember that reports for labs 3 and 4 due next week. Remember that reports are due before the beginning of the next lab. Okay. Today's lab. Today's lab is single resistor circuit, and today's lab is single resistor circuit, in which we will observe Ohm's law. Please download your spreadsheet from your group folder. And the resistor resistance measurement. No. Not this one I want another one. Oh. Resistor, resistance, single resistor. Here you go. That's the one I want. Okay. Let me walk you through this lab. And by the way, I have a lab that this lab is also recorded there in my YouTube channel. Videos. You can look for a P38 lab. Oh, wait a minute, playlist. Let's go to the playlist, physics labs. And should be a P38 lab here. Let's see. P38-2 is this one here. We have 2 versions of this lab. Let's see, this one is 32 minutes. That's the one you wanna. 32 minutes long. 2022 lab number 4 is the circuit with a single resistor. I'm going to put a link. The link to this lab is, for every lab that we cover here, I have a recording, like a 30 minutes long recording. If you want to watch it, if you have any questions, okay, you can watch the lab. Now let's go here. I don't need this one, but I need this one here. I'm going to walk you through how we do this experiment. And correction. Raw data, and I'm going to open one of those spreadsheets. Content. Here. Oh no. Let's see. Let me check one thing here. It's like I made a mistake of uploading labs that right. Interesting. Why is it doing that? I don't know. Oh gosh. Okay, go ahead. Lab group number 6. Make sure you delete. There's some graphs in there that I forgot to delete. Let's start with group number 6. Please delete your graphs in there. I want you to do that from scratch. Okay. Okay, that's spreadsheet of group number 6. Let's see the other groups. Yeah, for some reason we have this. Don't know why you have this link here. But yeah, this also has a, what a shame. Yeah, group number 4. Please delete the graph that's in there. You're not gonna need that. You have to plot from scratch. And that's group number 4. Let's see the others. Yeah, I do not know why we have this thing. Yeah, we all have it. And that's group number. Oh, have some junk here as well. What a shame. Yeah, that's group number 8 as well. We don't have group number 8, right? Let's take a look here. Yeah. Yeah. Some junk here that shouldn't be here. Group number 7. You also have a graph there at the bottom of the spreadsheet. Yeah, group number 2. You have a graph there. See what those links are all about. I don't know what this link is all about. Source break link. Break links. Yeah, I don't need it. Close. Now we shouldn't have group number 2. Might want to delete that as well. This one gonna be group number 3 and sign automatically cancel. I should have added link. Yeah. Yeah, it looks like every spreadsheet has those graphs there at the bottom. Group number 1 as group number 5 as well. Edit links. Let's see. Break link. For some reason, I have a link here to this group number 1 file. Break links. Hopefully, we do not have this problem anymore. And so, group number 5, make sure you delete that graph too. You don't need that. And group number 1 as well. Yeah. Delete the delete the graphs that are at the bottom and good. So hopefully we can get going now. 9. Oh, I didn't clear this one. Good. Now I got it. Good. So that's the spreadsheet here. The first thing that you're going to do is in this experiment is to measure. Let's see. Let's start with the materials, right? List of materials for this lab. First thing is going to be a resistor, one resistor. Okay. And the next thing that you're going to do, you're going to measure. I'm going to have here a list of material, and I'm going to put that procedure. Measure the resistance of the resistor with the multimeter, You already know that multimeters can measure resistance, can measure voltage, can measure capacitance, depend on the multimeter, of course, can measure current, can measure even frequency of a circuit. Okay, and in order to measure, so part of the material is a digital multimeter, or DMM. Very important device. You can use it to find out if you're running out of power in your battery, right? You can use it to measure resistances of different components. And I'm going to close this guy here and save it. Go. Take some time. Good. Okay, what else we need? We need a power supply. Power supply to provide voltage. Provide voltage to your circuit. And let's write it down. List of materials and procedure. Okay. Now cables. I'm going to tell you exactly how many cables you're going to need. You're going to need 1, 2, 3, 4 cables. 2 black banana cables. 2 black cables, 2 black cables, 2 black cables, and 2 red cables with banana plug. We usually use that. Let's take a look at this banana plug, how they look like. Plugs. Okay, that's how they look like. Here you go. That's the banana plug. They usually sell those things in black and red. They have other colors too. And we constantly use this type of cables to mount, to put together experiments. Okay. 2 black cables and 2 red cables with banana plug. Measure the resistance of the resistor with the multimeter. And then procedure, plug the red cable, the red banana cable in the red output of the power supply. So let me show you how a power supply looks like too. Power supply unit. Okay, here's a bunch of power supplies. Okay, they're different, but they have one special thing in common. They all have plugs that are red and black. See that? The red is positive, the black is negative. This one too, red and black. And they also have this yellow one here, but the most important is the red and black, red and black. They have everything, that's all every power supply has in common is those plugs, red and black. Notice that the middle one here is yellow, but this one is green, right? But consistently, the red and black, all of them have red and black. It has been established by standards that the red plug is positive, the black color is negative. So this thing is just like a battery, right? There's a positive terminal in red color and a negative terminal in black color. This other one too. Those power supplies are battery that can be adjusted, are battery that you can increase and decrease the voltage, their voltage. That's what those power supplies are all about. Okay, plug the red banana cable into the red output of the power supply. Next, and that's what I have here, my red cable with my banana plug. Banana plug goes both sides, this side and the other one. The plug here is fit to house the cable, the banana cable. Here's my resistor. Connect the red cable to the resistor. Okay, that's the next step. Connect the other end of the red cable to the resistor, the single resistor. One resistor, and then you're going to close the circuit. Black cable, black cable, black banana cable. Black cable with banana termination, we call it black cable with banana termination, connected to the black plug of the power supply. And 2 red cables with banana plug. Okay, of the power supply. And once you have done that, you completed your circuit. Okay. The diagram, the schematic diagram is something like that. The power supply is set at 10 volts. I have to write that down. Okay, and procedure. I didn't measure the resistance with the multimeter, plug the red button into the output. Okay, power supply. So what I have to do, turn on the power supply and adjust it to 10 volts. That's the procedure. Here is the diagram, And what you have to visualize here, you have to visualize electric charges moving in the circuit as though they were little cars, small little invisible cars moving in a racetrack. Okay, that's how you have to visualize. That's what we have to visualize here. And we can visualize that from that. Let's get that. Right, remember the, okay, the fat. Okay, right here. The fat simulation that I provided to you before, right? We're going to put that circuit again. The battery, right? I'm going to put a switch just for the case, just for the sake of using it. And I want to, yeah, here goes. See, I'm following exactly what's here in my circuit. Wire. Resistor. And wire. Okay, at this very moment, if you close the circuit, we have a current flowing through the circuit. That's the motion of the electrons. The conventional direction of the current is the other direction. This one that you see here. Once you have connected everything, you should visualize this type of motion in the circuit. What's gonna do next? Right now, we're not doing any measurement yet whatsoever. Okay. Turn on power supply and adjust it to 10 volts. The current should start flowing. The current should start flowing in the circuit. Okay. Next, what we're going to do, we're going to measure voltage with our multimeter. The multimeter there, they call it, looks just like this thing. I like to use this multimeter. I'm very familiar with it. Black and red, right? Black and red. Those yellows, I'm going to tell you soon what those yellows plugs are all about in the multimeter. Okay. Next, we're going to measure voltage. Connect the multimeter in parallel to the resistor. Okay. Connect the DMM, digital multimeter, in parallel with the resistor. You're going to measure voltage. Remember, you're going to measure voltage. Every time you measure voltage, you have to connect that in parallel with the element, with the circuit element. Okay, and take your measurement. Take your measurement. Take your measurement with the multimeter. You should read a 10-volt current. Okay, so there you go. That's how it looks like in a circuit diagram. It's a voltmeter. The multimeter is working as a voltmeter. Okay. And what else do we have to do? Oh, by the way, let's go to the spreadsheet, right? Raster, this one here. Okay, so how do you perform the experiment? I should have written it. We start with 10 volts. Start 10 volts, then decrease the power supply to 8, 6, 4, and 2.8. Okay. And as you change the voltage, you're going to measure the voltage, V1, voltage V1. You already measured the resistance, right? Resistance is here. So procedure, let's go to our procedure. Connect the multimeter in parallel, take your measurements with the multimeter. You should read a 10 volt voltage. A 10 volt electric potential, right? Take your voltage measurement. Take your voltage measurements with the multimeter. Okay. Here you go. Start with a 10 volt electric potential. 10 volt electric potential. Then change the potential to 8 volts, 6 volts, 4 volts, and some of them is going to be 2.8, others going to be slightly different, right? And take the voltage measurement with the multimeter. So what are you doing here? We are changing the voltage right here in the power supply. We start at 10 volts, take a measurement with the multimeter. The multimeter is going to read close to 10 volts because you have a single resistor here. You change the power supply measurement to 8 volts, and the multimeter is going to read 8 volts as well, at least close enough. 6 volts, 6 volts, 4 volts, 4 volts, and so on. Okay. Next, and that's what 1, 2, 3, 4, 5 measurements are all about. Okay. Next, what you're going to do? Next, you're going to invert the polarity of your circuit there. Whatever the red cable that was in the red plug is going to be there in the black plug. Why do we do that? We do that to invert the direction of the current. That's why we do that. Once we do that, the multimeter is going to read a negative voltage. Doing that is the same as doing the following. Don't need that. I don't need that. May need that. Must be here. Oh yeah, right in here. Here you go. Here's my voltmeter. Okay. Here you go. Negative and positive. Okay. Here you're reading 9 volts. So let's see. We can put a 10 volts. Yeah, I can put a 10 volts. Okay. We start at 10 volts. And the multimeter is going to read, 10 volts. I change the power supply to 8 volts. I'm changing here, power supply to 8 volts, and the multimeter is going to read 8 volts, at least close enough to 8 volts, and so on. Okay. Once you finish those measurements all the way down to 2.8, what you're going to do? You're going to change the polarity of your circuit. How do you change the polarity of your circuit? You can change the direction of your battery, for instance. Or just that's one way of doing that. Another way is just to get this cable connect to the other end, right? And now that I changed the polarity of the battery, the multimeter is going to read that negative voltage. And that's how we do in this experiment. I go change the polarity of the circuit by plugging the red cable in the black plug of the power supply. And by plugging the red cable and the black cable in the red plug. Okay. repeat the measurements in items 7A and 7B. That's what we did, and that's what we get right here. So that's what we did so far. Power supply voltage, that's displayed there in the screen on the power supply, voltage measured by the multimeter. All those values are very close to the values of the power supply. They don't have to be necessarily equal. Okay. So, and the goal, let's write down the goal too. I didn't write down the goal for you, right? Goal of this experiment is to verify Ohm's law equal to Ri. Okay. We already measured the resistance, we measured the voltage, and now we're going to start measuring the current. The current. Okay. Measuring. To measure the current, we must change the circuit configuration. Okay, and how do we do that? It's spelled out here in our diagram. We start with the power supply, red cable in the red plug of the power supply, starting from scratch, right? To measure the current, we must change the circuit configuration. Starting from scratch. Starting from scratch. We do the following. Okay, red cable to red plug of the power supply. Remember that in order to measure current, the multimeter must be connected in series, right? I'm going to put a note here. Voltimeters are connected in parallel. Ammeters are connected in series. Okay? And now it comes to the point that I'm going to tell you what those yellow plugs are all about. Those yellow plugs that you see about, that you see here, they are to measure current. This red plug that you see in the multimeter, they are used to measure voltage, frequency, and resistance. Because the ammeter must be connected in series with any circuit, the multimeter must have an independent circuit on it. That's why we have this separate plug. Okay, remember that? So going back here you go. We see that we connect the red, but you don't connect the yellow because we're not measuring the current. The yellow plugs here in the multimeter is to measure current. So after doing that, we get the black cable connect to the black plug of the multimeter. Okay, let's red cable to red plug. Let's see. To measure the current, we must change the circuit configuration. Starting from scratch, we do the following. Red cable to red plug of the power supply. Okay. Other end of the red cable to yellow plug of the DMM, digital multimeter. Okay. Black cable into black plug of the DMM. And that's what you saw right here. Other end of the black cable right? Where does it go? Well, it goes to the resistor. Connected to one end of the resistor. Okay. Finally, we're going to close our circuit. Black cable of the power supply to the other end of the resistor. Black cable from the black plug of the power supply to the other end of the resistor. And now we have this second circuit, different from the previous one. We use the second circuit to measure the current. Okay. Compare that. We'll see if I can have it. I want you to compare that with this other circuit that you see here, not this one. This one is better for now. Yeah. No, not this one. Here you go. Compare those two. See? Ammeter in series, voltmeter in parallel. Ammeter in series, voltmeter in parallel. Right? Series, parallel. Series, oh. Series, parallel. Series, parallel. Measuring current. And now you repeat what you did before. You start at 10 volts, decrease to 8, 6, 4, and 2.8. Okay? So start making your current measurements. Measure the current. Measure the current for voltages of 10, 8, 6, etc. Right? And that's exactly what we have here in the, that's the one, right? You did this one first, and now we are doing this one here. Note, see that I put I plus and I minus, okay? There's a reason why I put I plus and I minus. I plus, what I plus mean? I plus mean that the ammeter is directly connected to the positive of the power supply. Positive of the battery, okay? We do that to show to the students that it doesn't matter where the multimeter goes. You can put the multimeter here, you can put the multimeter here, you can put here, and it's going to show the same current. Almost the same current. Okay, and now what we're going to do, we are going to invert the polarity of the circuit. Not this one, right? Remember, never connect an ammeter in parallel to a circuit, or you're going to blow it up. You're going to damage. Okay, never connect your circuit this way. Only voltmeters are connected in parallel, not ammeters. Okay, here I have switched the polarity of your power supply. Switch the polarity of your power supply and measure the current for 2.8 volts to 10 volts. Those should be the negative values of the current. You should get the current reading should be negative, see? So we're done with all those three columns of the measurement. Next, what's next? Now we're going to reposition the ammeter elsewhere in the circuit and perform the same measurement. This is just to demonstrate to you that no matter where you position the multimeter, here you go, see that? the circuit, the measurements are going to be the same. And that's what I call the I plus measurement. I minus measurement. Why I minus measurement? Because the ammeter is directly connected to the negative of the power supply. Okay. So repeat. Okay, repeat. Let's see. Connect VMM to the negative of the power supply directly, the negative polarity of the power supply. Repeat steps 8F and 8G. Okay. And that's when you get the I minus current, which are going to be very close to the I plus current. Then what's next? Those are all measurements. What you see here are results. What I did, I took the average value of those two currents. Okay. What I did here was to get the power of the circuit, which is V1I. And what I did here is to determine the resistance using Ohm's law. So whatever resistance you got here is going to be similar to that you have here. What graph do we have to plot? You have to plot. Okay. You're going to plot V and I average. Okay. But remember, the V must be in the vertical. The I average must be in the horizontal. Insert. Yep. So that's Ohm's law in real life. Ohm's law in real life. There's a linear relationship between the voltage and the current, but there is one important detail here. You have to switch, right? You have to invert here your axis, because in this case the V is being plotted in the horizontal. You want the V to be in the vertical, and you have to switch the axis. How do you switch the axis? You go select the data, right? Edit. G becomes J and J becomes G. Okay, G becomes J and J becomes G. And now we are going to invert. Okay. Those numbers are so small, right? Make sure you adjust the font size. 9 size is too small for me. So make it 12 at least. Even 12 is small. I'm gonna get this one here. Font size 12. Let's make sure we have the right values here. Here should be I. Here should be V. Right? It goes all the way up to 10. Before, I didn't have anything like that, right? I have that, right? That's what I had before. I had the current in the vertical and the voltage in the horizontal. So I had to invert. Why? Huh, interesting. It's not doing it. Yeah, I gotta do that all over again. Huh, strange. Let's do it again. select data, right click, select data, edit. G becomes J. G becomes J, and J becomes G. J becomes G. Okay, and we double click here. Font. Font, at least, let's put 14, right? You know, and here to font. Size 14. I also want to change the notation here. Instead of scientific, I'm gonna put it like actual numbers. Decimal places, I should put 3 decimal places because it's in milliamps. Here, I do the same, I put numeric. I don't need to put, it's going all the way up to 15. I suggest that you go to 10, minus 10 to 10. Okay. Minus 10 to 10, and then we can adjust this one too, right? There is, it looks like there's a little bit of a, yeah, blank space here. We can go to 9. Axis option from minus 0.09 to plus 0.09. And I can also, to get it right, I can also change it my, major point. Oh, no, it's too much. It's too much. Let's put 0.03. See how it becomes encroached? We choose the proper division and we get everything nicely. Start at minus 0.09 all the way up to 0.009. Don't forget to put the units, right? Units, chart design, add chart element. Let's see how you're doing there, right? Primary horizontal. What is that? What happened here? Let's see. Let's do that again. Chart design, chart element, axis. No, axis title. We want axis title. Here you go. Axis title. And then axis title, the vertical, primary vertical. Okay. And then you can type it, everything that you have in there. Let me call you one by one, seeing if you're following, right? Roster. That's going to be 6. Download. Arthur Pacheco, did you download the spreadsheet? Okay, good. Next, did you plot your graph? Yes, okay, good. And don't forget to put the went back here, right? Don't forget to put the trend line too, right? I'll put here you go. The trend line indicates that the slope is 1,222, which should be the value of my resistor. It's not exactly 1,222, it's 1,197, close enough. Okay. That's a measurement with the multimeter, and that's a theoretical value for the resistance using Ohm's law. They are pretty close to each other. You want to know their percentage difference, the percentage difference between the experimental value and the theoretical value. You put it the slope value right in here, right? 1,000. How much was that again? 1,222. 1,222. I'm getting only 2% difference compared to the measured value. Okay. And let's go to our next student here. Roster. Janet Garcia. No, sorry. Let's go to the next. Elika, did you download the spreadsheet, Elika?
Yes, Professor.
Okay, did you plot the graph?
Yes.
Okay, and then the next question I'm gonna ask you folks, percentage difference. What's the percentage difference you're getting?
Working on that.
Work on that. What about you, Arthur? Did you get the percentage difference? Not yet? Okay, so working on that. Good. Next, Brianna. Is Brianna here? Brianna, I don't see Brianna. Yep, Brianna is not here. Next is Justena Youssef. Are you there, Justena? Working. Okay, did you download? First, I want to know if you download the spreadsheet. Yes. Did you plot the graph? Working on it. Okay, good. Next, Ashley Diaz. Let's see. Ashley is here. No, she's not here. So it's going to be a no. Natalie Espinosa. Okay, you download the spreadsheet, Natalie? Yes, okay. So let's see, you download the spreadsheet and you plot the graph as well, right? I want to know if you found the percentage difference. What about the percentage difference? You get a percent, you did that too? How much percent you're getting? What's the percentage difference you're getting? %73 is too much, okay? There's something wrong in there. 73% is too much. So try to figure out what's the problem, right? Okay, try to figure out what's the problem. Janet just joined us, right?
Yeah, I kept getting kicked off for some reason.
Okay, let me put attendance here. Did you download the spreadsheet?
Yeah, I got it already.
Okay, did you plot the graph?
Yeah,
What about the percentage difference? Did you get the percentage difference?
no, not yet.
Okay,
I'm
so you're
working on that one.
Okay. So good. Next. Randy, are you there, Randy? I don't see Randy here. Okay, he must have
Yeah,
left.
his connection was dropping out.
Okay, let me see. No, he has something else. He sent a message here. He had to leave, so I'm gonna put a star here. And next, Noor, are you there? See. Noor, hello, I can't hear you. Okay, I'm going to skip Noor for now. Kaylee Hernandez. Are you there, Kaylee? Yeah, yes to both. What about the percentage difference? You get the person not yet? Okay, working on that. That's good. Kennedy, you download the spreadsheet.
I have.
Okay, do you plot the graph?
Yes, sir.
What about the percentage difference?
I'm
You get
working
it?
on that right now.
Okay, thank you. Ryan Ong.
Yeah, I downloaded the spreadsheet. I did the graph, and the percentage difference that I got was 0.47%.
Okay, good. 0.47. Good. So you had to switch the axis, right?
Yeah.
That's right. Good. So we start working on the rest, right? What's the rest? The rest is the units and make sure the graph looks nice, right? The units and significant digits and the CL. Okay. 11:10, right? We need a break, right? We have been doing that for more than 1 hour. Let's take a little break. And I'll continue with Donia when we return. 11:10 right now. Break from 11:10 a.m. to 11:25 a.m. So I see you in 15 minutes. And let's see, I suspect that I didn't, let's see here. Okay, we're recording, that's good. I'm gonna pause. Okay, I'm back here, and let's continue with now it's Donia, right? I stopped that, Donia. Donia, did you download the spreadsheet?
Yes,
Okay, do you plot the graph?
yes, I'm still working on the percent difference.
Okay, good, thank you. Let's go for the next one, Vanessa Bonilla. I'm working. Okay, good. So she's working on the percentage difference. Thank you, Vanessa. Blanca Hernandez.
It will be the same from Vanessa.
Okay, working on the percentage difference, right? Thank you.
Professor,
Yeah.
could you go over the actually finding out the percentage difference? I think I'm kind of lost. Please, thank you.
Let's see, here you go. Okay, so you plot the graph, right, Elika?
Yes, I did.
Did you get the regression curve?
I did.
Equation?
Yeah.
Okay, you get the slope, okay?
Mhm.
And you type the slope right here. The slope values, and here are the units. Units are here, values are here. So you just type the slope right here. In my case, my slope is 1,222. Okay. And then you read the percentage difference here in this cell. In my case, it's 2% only. Make sense?
Okay, got it. Thank you. Yeah. Mhm.
Okay, who is next? Roster. Joshua Jimenez.
Yes, I'm still working on the percent difference.
Okay, so next is Alondra. I cannot hear you, Alondra. You need to turn on your mic. It's turned off. Working on the difference. Okay. Now Daisy. Daisy's here, right? Okay. Did you download the spreadsheet, Daisy? Okay. Did you plot the graph? Oh, 11%. Okay. So you got a difference of 11%, huh? 11.34%. Okay, you're group number 6. Okay, I'll check that. 11% seems a little bit high for this type of experiment, but I'll check it. And let's see. Yesenia, is Yesenia? No, Yesenia is not here. Leiblut?
Yes, I was able to plot the graph and I got a percentage difference of 0.68.
Okay, 0.68.
Yes.
Okay, and you did everything else, right? Let me check group. Okay, thank you, Leiblut, and start working on the rest, right? So you need to work on the units, need to work on the sig fig, and need to work on CL, right? And everything else. The percentage difference, working on that now. Okay, thank you, Noor, and you're working now. Okay, in your case, Noor, did you do the units, the significant figures, the CL, and so on? Okay, good. So Noor, gonna put here Y, and Y for yes. And let's take a look at group number 6 spreadsheet. It's a little bit high, 11%. Okay, Noor. Okay, Daisy. Let me check if there is something wrong with that. We're gonna get out of that. Oh. 6. Whoa. Oh. Huh. Spanish. Take the notes. Okay, now I can. The next one, group number 6. Okay, group number 6 is V1 and I average. And I have to change select data. G becomes J. And J becomes G. And let's put the trend line here. 2,351. Okay, 2,351. Yeah, I'm getting 11.35% too. Yeah, okay. So yeah, we don't usually get this high difference in this type of experiment, but it is whatever it is, right? So stick to that and 1132. Now plot V along that V or V1. I don't need that. I don't need that. Now, it's V1. Okay, it's V1. Plot V1 along the y-axis and along the y-axis, and IAVG along the x-axis. Okay. Sharing the screen, right? Roster. So let's go back to Pacheco. Pacheco, did you get the units? Up to Pacheco, group number 1. Yeah, oh yeah, that's right. What the percentage difference you got? Yep, 0.78. That's the type of percentage difference we get for this type of experiment. Okay. Did you work on the units? Did you finish the units? Doing it right now. Okay, working on that. What about you, Elika?
Yes,
You get it?
Professor, I got 0.78 as well for the difference.
Okay, good. And what about the units?
Working on it.
Good, thank you. Brianna is not here. Justena Youssef. Did you plot the graph, Justena? Yes, okay, but okay, so you gotta be careful, right? So 78% is a big difference, right? I guess you meant the 0.78%, right? And not 78%. Okay, 0.78%. Okay, good, thank you. %. Ashley, not here. Natalie, did you figure out what was the problem with the percentage difference? Yeah, 0.73. Okay, thank you. 0.73. What about the units? Did you work on the units as well? Yes, and the sequence figures. Oh, wait a minute. That's Janet, right? Let us finish with Natalie here, Janet, and I get to you. Here you go. Did you finish the units, Natalie? Working. Okay, good. And I need to go back here to Justena. Justena, did you finish the units? Okay, working. Good. And now it's you, Janet. Did you finish? Did you get the percentage difference, Janet? Yes. How much did you get? Same as Natalie. Okay, good. 0.73. What about the units? Are you working on the units? Okay, good. So Randy left. Okay, Noor, did you manage to finish the percentage difference? Not yet. Okay, good. Next, Kaylee, did you finish the percentage difference? Not yet. Okay. What about Kennedy? Did you finish the percentage difference?
I'm working on it, but I finished the other things instead.
Okay. So you did the units, you did the sig figs, right?
Confidence level as well, yeah.
Okay, good. So, okay, so let's go for our next one. Ryan, you got 0.47% for this percentage difference, right? And did you finish the units, Ryan? Working on it. I'm just making the graph better right now. Okay, good. Improving the graph. Next is Donia. Donia got okay 0.47, just like Ryan, right? And what about the units, Donia? Did you finish the units? Oh, she worked on the units. Okay, good. Okay, Vanessa. Vanessa Bonilla. Did you get the percentage difference, Vanessa? I don't hear from Vanessa. I'm gonna put a star here. Let's go for Blanca Hernandez. Are you there, Blanca? It's like Blanca walked away. Oh, okay, I'm away from the computer. Okay, well, tell me. Okay, so whenever you return, let me know. And Joshua Jimenez.
I got the sig figs done and all the other stuff. I just had a quick question. I kind of forgot how to get the slope again. You mind show me real quick?
Yeah. Did you? So you did the units? You working on
Yeah,
the
I got
units?
everything done. I just need to get the
Okay.
percentage difference, but I forgot to do a slope.
Percentage difference. Let's do that together. here you go. Here's my graph. I'm gonna plot V and I average, right? So when we have this order here, V in the left and I average on the right, you're gonna get the V in the x-axis and the I average on the y-axis, okay? So you have to fix that. You don't want the V in the x-axis, you want the V in the y-axis, right? So
Yeah,
what
I
do
did
you
switch it already.
Okay, you already did that?
Yeah.
Right click, select data, right series, edit. I'm gonna edit, from scratch. Let's do everything. J here, G there, and G there. After you do that, now you can plot the trend line. Trend line and display the equation chart. Okay. Here you go. Here's the trend line. That's the slope. Right?
Oh, that's the slope right there. Okay.
Yeah, that's the slope and that's the intersect, right? So the slope is what multiplies the x, right? And that's what goes here in this last table.
Okay, I got it.
And now I'll be back. I'll get back to you. And what about Alondra? Did you get the percentage difference, Alondra? Working on the units, got 1.35% as well. You mean 1.35, 1134, okay. Alondra. So let me see, working on the units, you're working on the units. Good. And the last one here, Labelud. Did you do the units?
I'm working on the units.
Okay, good. So we have another 20 minutes to finish all of that, right? I'll give you a little bit more of time. If you're done, I can see some of you are done, right? You can leave. If you want to continue working on the rest, you can stay. I'll be here to help you out.
Professor, can I get help for sig figs for lab number 3? I couldn't figure it out.
Okay, which group number are you?
Number 6.
Number 6. Okay, lab 3, right? It's not lab 4, right?
Yeah, lab 3.
Group number 6. Oops, wrong. Group number 6. Okay, here you go. Okay, so did you do this one here? The nominal value?
I can't see your screen.
Oh, yeah, let me start sharing it. Here you go. So that's the first table, this one here.
Yeah, I couldn't figure out the sig figs.
Yeah, let's start with this one, right? Let's start with this one. This one here is the color code, remember?
Yeah.
Okay, the color code has only 2 significant digits. Remember that I mentioned that?
Oh,
Only
I thought it
colors
was
for the numbers.
3. I thought it was 3 because there was 5 colors.
No, actually, it's 4 colors. Okay, some resistors have 5 bands, have 5 colors, but the resistor that we use at the college has only 4. So it's 2 colors for significant digit, one color for the power, one color for the tolerance. So you have to display 2 significant digits here.
Okay.
And because you have 2 significant digits here, you must have 2 here and 2 here as well. All those 3 columns are 2. That's the only one that you had a question?
No, and also for the DMM resistance, I was trying to figure it out from the chart, but I couldn't.
Okay, so let's take a look at the chart of the resistance, right? Let's see. P38 significant figures right in here. Resistance DMM. That's the first table, right?
Yes.
Resistance DMM. So it goes according to the value of the resistance. From 1 to 9.99 ohms is 3 sig figs. From 10 to 99.99, 4, right? And so on.
Oh, okay. So if it's like, for example, the 14,000 one, there would be 5 sig figs.
Yeah,
Oh,
14,000
okay.
is between 10,000 and 20,000. Okay.
Okay.
Any other one?
No, that's the only ones I really had questions on.
Okay.
And it goes the same for the other ones, right? For the other
Yeah.
table. Okay.
Yeah. Well, but wait a minute.
Except
The
for the
other table,
inverse one.
you gotta be careful, right? Those are all measurements, right?
Yeah.
Those are all measurements, right? Whatever is measurement, this is a measurement as well. So it goes according to the table, but not here. Here you have what? You have a
Oh, from the other table.
result.
Okay.
You're summing one with the other.
Mm-hmm.
Okay. So you gotta use the rule, the summation rule.
Okay.
Okay. Here is the same thing. Those are measurements. And here is the division rule. Okay. Here, is the division rule that you had from the previous table. And then here's going to be the summation rule.
Okay. And then that goes the same for units, right?
What do you mean goes the same for units?
For units, it would be 1 over the sorry, I forgot what the symbol's called.
Ohm, 1 over ohm.
Yeah, got it. Okay, that makes sense.
Okay.
Okay, thank you. That was all I had.
Let me close that. So let's see. I'm curious about those students who were working in the percentage difference, right? Let's see, Noor, are you there, Noor? Okay, what about Kaylee? Are you there, Kaylee? Like Kaylee left, huh? Okay. And Kennedy, did you get your percentage difference?
I was actually just in the group chat. We switched back to the last lab, looking at what was just brought up. So with the 2 significant digits, I would just alter. So say I have 162, I would just make it 160.
Okay, so which lab are you referring to?
I'm sorry, lab 3, we switched back for a second, and I was asking my group mates questions.
Lab 3, group number 3?
Yeah.
Okay, so let's see, corrected, 38.
Right, yeah, because I was kind of confused on the significant figures as well, and it looks like we need to clean up.
Okay, so let me get your report. Is that the one wrong? Yeah, that's the one, lab 3, right?
Yes.
Lab 3, group 3. Okay, so here you have to display 2 significant digits, right? And you're asking a specific number. Which number are you asking?
Excuse me. Let me pull it up. So Oh, never mind. They're all right there. It's 2. Never mind. I had looked over at the lower value column and picked out the first number, but those you said all 3 under the nominal value would be 2 significant figures or just a center?
All of them should be 2 significant digits because they all have only 2 color bands, right?
Okay, so the lower and upper values.
Lower end. Oh, the lower end. Oh, yeah, all of them. All of them is supposed to have 2 significant digits. Yeah, that's right.
Okay. So say I have 162, I would just input 160.
Oh, you gotta be careful, right? You gotta be careful. You gotta display. Here you go. If you
Sure.
take 160 and display like that, right? You are displaying 3 significant figures here, right? Right? You don't want these significant figures.
Okay, because I thought if there was a decimal, it would make the 0 count, but if there wasn't a decimal, the 0 wouldn't count as a significant figure.
Well, the correct rule for that is that zeros to the right of a significant digit is a significant digit. Okay, that's the correct rule.
Okay, I messed up. I thought it was if there was also a decimal. In
No, it
front of
doesn't matter. It doesn't matter. If you display like that, 0.0, if this 0 is still considered a significant digit, right?
Yes. Okay. So
yeah.
So then
how
I apologize. Go on.
Yeah. No. I want to hear your question.
Okay. So just like I was saying, so for the numbers that are like 162, 114, how would I satisfy the significant figures?
Okay, you write in scientific format. Okay, so right now you're displaying 3 significant figures, but you have to display only 2. What do? You write that down in scientific format. Scientific, and then you cut down the decimal places. Now I have 2 significant figures, and the number is the same. Okay.
Oh, okay.
2 figures, and the number is still 160.
All right. Thank you so much. I really appreciate it.
Okay.
Professor, I have one question for lab number.
Number?
Lab number 4.
4. Okay. You're group number 7, right?
Group 7.
Group 7. Let's go here. Yeah. Okay. I'm here.
So for the significant figures of negative number, how do I find those? Like, because there are negative numbers. Like, for example, for bold 1, there is.
Yeah. Okay. You use the positive numbers in the table. Okay. Use the positive numbers in the table. Right in here. You treat the negative number as though it were a positive number.
Okay.
You have the same number.
Okay. So as like they were positive. Okay. Okay. Thank you.
Okay. Pagamento. Vamos pause that before it gets too large. See.